Hello, this is Philip Myers of PEMY Consulting. Welcome to Strength of Materials Part 9 on General Stress and Strain. We are at the point where we can now talk about general stress and strain. We won't go into much detail, but we will cover some of the basic ideas and concepts which should help you to understand the behavior of steel a little better. If you work with finite element analysis modeling, this knowledge will help you improve your interpretation and understanding of how finite element analysis modeling works, its strengths and weaknesses. So our learning objectives are as follows. First, we have to make some assumptions. We assume that the material is isotropic, that is, no matter what direction in the material you're considering, the material behaves the same. Another important assumption is that we are talking for the most part about stresses and strains below the proportional limit, that is, the behavior where the material is elastic. We'll recap Hooke's laws for uniaxial stress. We'll recap shear with examples of single and double shear. We'll define shear strain and the relationship between strain and shear stress. Then we'll compare normal strain with shear strain. We'll define Poisson's ratio. We'll cover the basic concepts of plane strain, and then we'll talk about the generalized Hooke's law. The uniaxial strain illustrated here is a simplified version of the real world, but it works to improve understanding. The bar has constant cross-sectional area so that the stresses are reasonably uniform at any cross-section in the bar. Given these constraints, the 1D Hooke's law states that the strain is proportional to the stress, that it is linear within the proportional limit, and that the strain is the dimensionless fraction representing the relative change in length. Strain would be 0 if there is no stress and consequently no length change. Negative if there are compressive forces acting on the bar causing it to shorten, and positive if there are tensile stresses causing it to elongate. Note that below the proportional limit, the relationship given by Hooke's law is linear, and that is represented by sigma equals E epsilon, where E is the constant of proportionality, Young's modulus, epsilon is the strain or relative length change, and sigma is the stress. Here we have a quick review of shearing stresses. Assuming the stresses are approximately uniform across a pin, which is shown by this rectangle, and the stresses shown here as being uniform throughout the cross-section, we can compute the shearing stresses by the formula shown, provided we know whether we are dealing with single or double shear. In single shear, the plane being stressed is shown by the red line. In contrast, in double shear, for the same forces acting on the bars, we have two planes and thus twice the area. That means that the stress is 1/2 as large in double shear as it is in single shear. That's reflected by a factor of 2. So the formulas are the same with the exception of the factor of 2. I will now describe the ideas associated with extending Hooke's law to 3 dimensions. This is called generalized Hooke's law. It addresses the behavior of materials when there is a triaxial stress state. The important assumptions are that the material is isotropic, meaning that it behaves the same way no matter what direction you're considering, and it's linearly elastic. That means that it's within the proportional limit. Let's consider the x direction. If we have a stress in the x direction, we get the strain in the x direction, which is sigma x over E, but we also have, according to the previous slides and according to Poisson's ratio, contractions in the other 2 dimensions. In the y dimension, we get the strain negative nu times sigma x over E, and we get the same strain in the z direction. Now let's consider the y direction. If we have a stress in the y direction, the y dimension will change by sigma y over E, but the strain in the x and z directions are nu times sigma y over E for both directions. Finally, if we consider the z direction, with the stress we have sigma z over E, and then nu times sigma z over E in the other two directions. These formulas can be cleaned up and more easily recognized and used if you pull out 1 over E and take it times the quantity sigma x, y, or z, whichever dimension you're first considering, and subtract off nu times the axial stresses in the other two dimensions. Typically, the uniaxial stress version, or 1D Hooke's law, can be used, but when you have a biaxial or a triaxial stress state, you really should use generalized Hooke's law. Now, we haven't derived it, but the formula for the shear modulus is E over 2 times 1 plus nu. The formulas for shear strain, which is a change in angle, for example, in the xy direction, is tau xy over g. We have similar changes in shear strain for the other two dimensions. Notice that there's no term that involves the other planes, so the shearing strain is only affected by the squeezing across the pairs of planes as shown here. So gamma xy has no effect on the xz plane or the yz plane. It's important to distinguish between displacement and deformation. This picture tells it all. A particle within a body can be displaced, but it can also be deformed. So, for example, point A is displaced, but to consider the strain, at least engineering strain, we take 2 points that are separated by a very small distance and see how much it stretches. And so the strain would basically be this formula. Strain in many ways is similar to the way stress behaves that we looked at earlier modules. The key properties of strain apply at a point and derived by taking small elements of the material. A line segment can change length, and that's considered normal strain. So you can take this body here and stretch it into different directions, and these length changes, which are a function of angle, of course, are the normal strains if you're looking at the corresponding straight line element. The angle between the segments changes, and that is the shear strain. So you can see that, for example, this second one here had positive shear strain. If we decompose strain, we can see that this is simple shear. This block of material is squeezed as shown here. In pure shear, we can see there's symmetry where the shear is acting equally on both orthogonal axes, and we're getting a shape that's a rhombus. And then, of course, this is pure rotation, so there is no shear strain. We're rotating the coordinate axes a little bit. So any arbitrary shear strain can be made equivalent to pure shear plus pure rotation. This is getting beyond the scope of what we want to talk about, but it helps to have some of these images in mind when considering strain. That concludes our section on stress and strain. Thank you.